Hello, everyone. Good afternoon. My name is Jack Zhang. I'm a cloud and storage architect at the Intel non-volatile solution group. Today, I'm give a introduction about my work on the mediumware smart storage. They call it mediumware smart storage engine. Basically, this engine understand and approve the SSDs, 3D cross-bond, QLC, TLC, apply different algorithm. Legal statement. Okay, overview. I mean, on the top, on the left side, it says typical system, I mean, application user space, in user space, and you application through file system to manage the drive, kernel, or SPDK. We typically see some issues or problems from customers. They're saying, hey, why do I not see X number of times improvement when I plug in Optane and replacing the flash SSDs? The second one is reshipping writes into large data set and sequential write to the QLC requires additional software investment, and the implementation can be different from application to applications. If there are any generic solution to support that, so I can better leverage QLC low cost benefits, right? So basically, we developed the user space, a piece of software in the user space. We call it SSE, Smart Storage Engine, mediumware Smart Storage Engine. So basically, this piece of software, lightweight software, can identify and classify different SSDs by their tab, medium tab, and build inclusive data sheet, inclusive data structure, the algorithm accordingly. So basically, for example, for Optane 3D crossbound, I want place data with writing place instead of append and write. Well, on the flash SSDs, I want data to append and write, especially for QLC. I want append and write to the QLC. So make sure the data is sequential, right, to the drive, to the QLC drive. So basically, we do smart, intelligent data placement, out shipping. On top of that, we have key value. This is SSC is key value based, built on the key value. You use key value to manage the drives. We also developed the, on top of this, we can support virtual file, virtual block interface. Software architect. So basically, we want to design a lightweight piece of software. We don't want to cause too much CPU custody in the user space. We don't want to cause too much CPU, and as well as memory. DRAM. From the bottom, we see NVMe driver and SSDs. Right, those are not is the standard. We're not changing anything on NVMe driver. We're not changing anything on drive side, like firmware inside the drive. Optane SSD or anybody's flash SSDs. This is not like open channel and DNS. You have to make sure you have to modify to make a special firmware to go with those open channel, right? And the module on the top, we have key value. Yeah, we have key value engine. We use KVDB to manage the drive as KVDB. On the interface, let's talk interface. We developed a virtual file system, a virtual block, in addition to key value. Basically, for the virtual block, you can see one single block interface by wrapping Optane plus QLC. You see /dev virtual drive 1 or virtual drive 2, but under that drive, you got Optane plus QLC layered two drives. So basically, we can run FL and with no difference as the active physical drive. We have mapping table. That's a very important part. Is since we do sequential write flash to the QLC or flash SSDs, we need a table, a mapping table. This is not logical to physical because we don't change anything. We don't know physical address. This is basically a logical to logical mapping table. It's in the memory. We have GC manager because we sequential flash data. At some point, we need relocation data. Volume and tier two. Volume is single layer drive. You can play with just one Optane or couple of drives, just one layer. Tier is fast plus slow, basically Optane plus QLC or TLC. I mean fast drive plus. It can be that layered. And then there's other two under development and different blue color, telemetry and utility. This is for the debug purpose. Instead of using special tool, we can intercept the workload and talk to the drive, doing some for the online debug. Also, we developed starting doing this workload AI engine. The idea for this is we want to understand the workload pattern, we analysis those pattern, and do inference. So basically, we can based on what we learned, we can do better optimization on the different workloads. See, you run something like 2-3 hours or maybe a couple of days. You learn that pattern, and then that guide you to do different data placement. Okay, that's the basic architecture. I only have 20 minutes, so that's basically what we have for this. So evaluation proofs. We are SSE mediumware smart storage engine. We want to compare with the medium unware engine like industrial very good open source or XDB. So we want to compare that, and we also want to run this engine on different SSD medium. So basically Optane, QLC, TLC. First, we compare smart storage versus XDB. On the left side, you see the operation per second. Basically, we use this is we run DB bench with the in this special case this task we have key equal 23 byte, value 100 byte. So we run 1 billion KB pair, and this is like mixed workload 50-50. On the operation per second, if we don't have this, so basically you compare when you compare with plugging Optane into the RocksDB and replacing P4510. P4510 is Intel DC TLC drive. We only see, I mean, this is basically a lot of customer complaint. It's only like 10%, not much difference. Then we are plugging this SSE smart storage engine and compare. We can get minimum 57% improvement on bandwidth. When we look at the right side, this is on the read quality of service QoS. You can easily see, I mean, without this software, you can see pretty much Optane and TLC has similar performance, right? 10%. Yeah. I mean, 1.1 times or 1.2, and some point like this case, 3.9 latency, even the Optane is higher than TLC. I think this most likely. Those most possible likely is the RocksDB itself overhead. When we replace RocksDB with this smart storage engine, you can see at least 4 to 6 times better. For the 4.9, I got 40 times, sorry, 40 times better. 40 times to 57 times better. That's a huge difference. So basically, it could be understood this smart storage engine is single lightweight and manage the drive and maximize the 3D cross-point capability. And then we also running this engine with different SSD medium. You can see QLC, TLC, and then tiered Optane plus QLC, Optane plus TLC, Optane itself. One at least read latency in the QoS. Since we flash the data to the drive sequentially, we avoid garbage collection or data relocation inside that. So basically, when we compare the WAF with individual drive, here QLC, TLC, or Optane plus QLC, QLC, there are almost no data relocation. Means WAF close to 1. So basically, there's no garbage collection. That means so let's go back a little bit. So when people see the drive has long tail read latency on a random read-write workload, that typically the reason for that typically is because when the garbage collection kick in, your read latency, your especially tail 99, 29, 39, even 49 latency going to jump higher because the garbage collection prevent the software, the firmware, give back your data. Well, we change that by sequentialize the data to the drive. There's no garbage collection, so your read latency going to be pretty much close to the read spec. Yeah, of course, it's lower because you still have sequential write workload. Because you don't have garbage collection, your read latency, QoS, going to be much predictable. In our case, we can easily limit that 3.9 to less than 1 millisecond, no matter what kind of drive, even QLC. This is still 50-50 random read and write, no DB bench. I think that's gives huge improvement for the drive itself and good for the applications. It's very predictable from a read latency. On the top, we see the write latency because we merge data and sequential write to the drive. So when you do single write like QLC, TLC, you can see the write tail latency is very big. Like TLC, I got 3.9 got 8 millisecond. QLC got 15 millisecond. But once I got plugging the Optane, the Optane in the write path, we cannot use. We do when Optane plus QLC, Optane plus TLC, we use Optane in the write path. So that dramatically improves the write latency. So Optane plus QLC, you can see for the 3.9 latency is 4 times better than TLC. And Optane itself is, of course, can be 8 times better than TLC. So we use TLC as baseline here, or baseline use TLC. And then you see the bandwidth for TLC, from TLC move to QLC, got almost 2 times better. And Optane plus QLC better than TLC. So you can see the almost increased performance increase by using better medium. Yeah. I'll emphasize a little bit on Optane plus QLC because one, I got faster performance, better performance, a little bit expensive. The QLC is low cost by using reasonable ratio. The ratio like we use on this test is 5%. So basically, that 5% of the capacity can be absorbed. The cost can be absorbed by the gap between TLC and QLC. For example, on this example, like we use 375 gig Optane plus 8 terabyte QLC versus 8 terabyte TLC. The Optane plus QLC cost is very close to TLC, but we got better performance on the bandwidth, the read-write latency, and QoS. So that helps a lot for the two things people want to do, especially for CSP customers. They want to improve the performance. They want to reduce the cost. Okay. Conclusion. So Smart Storage Engine basically is a mediumware. It's a high performance. We're still under development. It's high performance, effective storage solution that can release power of the SSD capability, the medium capability. It is inclusive design that reduce application burdens. We are independent from applications. So application take care of their application user program, and we take care of the hardware to make sure we get maximum. We release the hardware capability to the application, so that can encourage people. The CSP. The customer to invest on new medium technology, buying Optane. Of course, by combining those two, faster dry Optane and lowest cost QLC SSDs, this engine can be growing. Basically growing demands from the cloud customers. I need a better performance. I also want to drop the cost. Next, we are under development. We're trying to design this SSD library to be a standard. So you really need to less work to plug into the applications. And then we also want to do user space module. Since we're already in the user space, we want to integrate somewhere in the SPDK. So basically, we bypass kernel. That's one under development as well. So we want to standardize virtual file and a virtual block interface based on the customer requirement. We also this one has been I didn't have the brought the data here, but we're trying to replace the file system under RocksDB. We're trying to define, it's called mediumware RocksFS. Replace the ESD4 or XFS file system. And then under that is this smart engine. So basically, RocksDB on top and bypass file system by using this engine. So the RocksDB is going to be a mediumware engine or RocksDB. We believe that's going to, the early data shows is it already improved the performance. Open source. will not develop something Intel always doing reference design. This is going to be reference design, going to be open source. We plan to deploy, push out this this code to GitHub in next 1 or 2 months, probably 2 months. Currently, this code has added a private GitHub. We can invite you to check the code, look at the code. Yeah, with that, I'd like to thank you very much for attending this class and send us your feedbacks. Thank you. And then